So welcome, Estefani, Fanry, Lexi, Regni, Susanna, Adam, and welcome, Diego. Thanks for coming. Let's jump right to the quiz. Okay, so the quiz is the following. Locate and classify any critical points using the first and second derivative tests. X cubed plus y cubed minus 300x minus 75y minus 3. That's our function. So what's our first step? So how do we start?
Find the gradient.
Yeah, we need to find the gradient. So I actually did some copy and paste while you weren't looking, and I can edit. I think this is nicer to make it pretty. So I need to find the gradient. So I'm going to write grad f equals. And what's the partial derivative with respect to x? Yeah, 3x squared minus 300. And what is the partial derivative with respect to y? Yep, 3y squared minus 75. Okay, and what do we do with that gradient? What's the point? So we found it, it's pretty. So what's the point?
Set it equal to 0 to find x
set
and
it
y.
equal to, and I like to say the 0 vector to remind yourself this is a vector, not a number. So we're going to set it equal to the 0 vector. Any questions so far? Okay, so I hope that you can maybe even do this in your head. Can you tell me what x is?
Positive negative 10.
Yeah, plus or minus 10. So note that x equals plus or minus 10. And what is y?
Plus or minus 5.
Yep. Y equals plus or minus 5. How many points do we get?
I got 4 sets.
Yeah, we're going to get 4 points. 4 points. So our points, our critical points, right, CP for critical points, are negative 10, comma, negative 5, comma, and I'm going to copy and paste, I think is the easiest way. We can drop the second negative, we can drop the first negative, or we can drop both negatives. And those are our critical points. Any questions on that? Okay, so we've now found the critical points, and notice, it's very differentiable, so there's no other things to look at. All right, we just used the first derivative test and found the critical points. What does the second derivative test say? What's the process now? Do you remember?
Like fxx times fyy minus fxy squared.
Yeah, I like to remember it as writing the Hessian down. I will tell you that matrices are really important for, especially if you can do if you can do more STEM stuff, more math, and, then matrices come up a lot. So let me write it as the matrix. The partial with respect to x twice will be, hopefully you can see 6x. Partial derivative with respect to x and then y is 0. The partial with respect to y then x is also 0 because it'll always be symmetric. And then the partial derivative with respect to y twice is 6y. And then the determinant, D, so D stands for determinant, is equal to 36xy. Any questions so far? Okay, so now what we can do is we can go ahead and use our second derivative test. So I'm going to do these one at a time. So let's start out with -10, -5. What is D? Positive or negative? That's all I care about.
Positive.
Yeah, D is greater than 0. Okay, it's 36 times -10 times -5. I don't care what number it is. I care about its sign. And 2 negatives make a positive, it's positive. All right, what does that tell us? So who remembers what it tells you when D is positive?
That it has potential to be either a maximum or a minimum.
Exactly. When D is positive, it's a maximum or a minimum. Okay. So what's the next thing you have to check to decide whether it's a max or a minimum?
Plug it back into like the formula. That's what I did it differently. I didn't use the Hessian method. So I basically just plugged it back.
Okay, you had to give me a D. If you didn't give me a D, then it didn't count because that's not the second derivative test. I didn't require the matrix, but you got to have the D because the D is the second derivative test. Yeah, you plug into fxx because that's what the theorem says. That's what the second derivative test says. And fxx, remember, was 6x, and that's negative. If fxx is negative, then what do you say about the critical point? If D is positive, yeah, that makes it a
maximum.
Yeah, relative max. Any questions on that? Okay, now what I'm going to do, I'm going to copy and paste and change what I need to change. I think it's the easiest way. So let's do the next one, which is -10, comma +5. What do you say about D this time?
It's negative, so it's probably a relative minimum. I mean, it is a relative minimum.
Okay, let's slow down. Let's slow down. D is negative. When D is negative, what does the second derivative test tell us? Not relative minimum. Yeah, it's a saddle point. Right, that's all part of the second derivative test. Very important to have that down. Okay, now let's do the next one. And if you take the -10 and make it a -5, then if you plug in, again, if you plug in 10, -5, you get a negative number. 36 times 10 times -5 is negative. And it's still a saddle point, same reason. Any questions on that so far? Okay, and then the last one. Let's look at what happens when we have +10, +5. Then now if you plug in to our D, we get a positive number. Any questions on that? What about fxx? Yeah, fxx is positive because remember it's 6x, which is just 60 in this case. So that's greater than 0. And when D is positive and fxx is greater than 0, then what do you get? Yeah, we get the relative min. Okay, by the way, what would you have done if D had been 0? Am I strict on saying relative? You don't have to say relative. You could say local instead. Okay. Yeah. So had D been equal to 0, then you would just get mad at me. I wouldn't say sob. Friday, you sob. Why'd you sob Friday and not sob today?
Actually, I had a question about that, Larry. What would we do? I mean, we just tell you that it fails, or 'cause we can't
Yeah, I
ask you?
mean, right. So the question, what would you do in which situation? There's two situations. One is you're in class taking a test or doing a homework problem or something like that. And the other is called the real world. Which one do you mean?
I suppose I care more about the test right now.
Yeah, on the test, then you would just say test fails and give up. Okay. And what I would probably do if I were you, especially the instructions are saying classify the relative extrema, I'd look for your mistake. Because I wouldn't do that to you. Does that make sense? Okay, so that's the first thing, is I wouldn't do that to you because it wouldn't be fair, because you don't know how to do it. Now, how about the real world? What would you do? Because this is an important thing.
I'm hoping that at the end of the quarter we figure out what to do. Maybe
No, you already know how to do it. But not for tests. For real world, you know how to do it.
take a small step to the right and left and figure out our derivative.
Yeah, kind of basically, except that, sometimes we're talking about not steps, we're talking heat or something like that, or, electromagnetism or cost or something like that. I'd go to CalcPlot 3D, graph it, and look to see, does it look like a max or does it look like a minimum? Does that make sense? Or does it look like neither? Yeah, so that's what I would do in the real world. And even in the real world, on the one we just did, in the real world, you also want to graph it, because you always want to, especially if your job depends on it or lives depend on it, then you got to get it right. So you do it in multiple ways and make sure that you double check yourself. Does that make sense?
Yeah, for sure.
Yeah.
And Larry, I was curious, this question I felt like stated whether or not we were looking for the relative mins and maxes. So I only wrote max and mins. So should we always classify whether it's relative or global just to
Yeah.
be safe?
Yeah, you should, because they're different.
Well, I felt like the question kind of insinuated, but I suppose you're right.
Yeah, it's ambiguous if you just say max or min, because relative and absolute are different. Does that make sense?
Yeah, I think I just want, it to not matter, but I see it does.
I'm not going to take off points on the quiz, but I'm just telling you that if it was a 10, if it was like 10 point for a single thing that you did, then I might take off 1 point, but not a lot. Does that make sense? So yeah, but relative and global are very different. So you want to make, or very different concepts. So you definitely want to specify what you're talking about. And in the real world, they're really important, because the relative often makes you think you have the answer and then you don't. And it turns out you screwed up. Okay, gets you into big trouble. You can kill people, that kind of stuff. Okay, one of my roommates, in fact, did this kind of stuff. Fortunately, he didn't kill anyone because he knew what he was doing. And his job was safety at amusement parks. This was pre-COVID, so you can actually go to an amusement park. So he looked at roller coasters and stuff, and he did the engineering and the math. And you make a little mistake and you kill someone. just to remind you want to do things right. Okay. Anyway, that was what my roommate ended up doing. Was he was the national certifier of safety for amusement parks. It was kind of cool. It was all engineering. Okay. Anyhow, any questions on this? Okay, so that's it for the quiz. So let us jump to, are there any questions about anything else?
There's a couple of questions about the homework I have, but I don't know if you want to wait till office hours.
Yeah, if they're long, we could do it in office hours. If they're
Yeah.
cookies.
Well, there's a couple, like a couple absolute minimum and maximums. I ended up having to use Lagrange multipliers from today, like to figure it out. And then there's a couple word problems that I just can't figure out.
Yeah, so if you don't have Lagrange, by the way, it's Lagrange. That I wouldn't take half points on, but I might also tell you the right way of saying it. If you don't have Lagrange multipliers, you can do it, but the algebra becomes a bit nasty. That's all. So you just have to substitute and then plug in. Whereas Lagrange multipliers is what we're doing today, that we'll find out there's a better way. And in fact, the problem is that some of these problems probably didn't need to be in the section you did. They should have waited until the next section. But I'm not the one that wrote that section, so I probably should have checked. I trusted my colleagues, which is always a mistake. Yeah, I had a lot of emails about it. But again, you do need to know how to do it, especially once we have Lagrange multipliers. Okay, any questions though? Okay, we might have time at the end too, and that might be a good time to ask longer questions. Okay, I want to get into regression analysis. Let me ask you a little survey here, and you have to answer. It's not a hard question. Have you taken statistics? I know I have one person who's not here anymore. I mean, he wasn't able to make it today. He's just not here today. Okay, so some of you have, some of you haven't. Okay. And so in statistics, whether you took it in high school or you took it in college, you learn about regression analysis, right? If you didn't, then I need to talk to your old teacher. So you learn about least squares regression and stuff like that. Okay. All right. Did your teacher tell you how to actually do it and why it works in terms of the formulas? Or did the teacher just say, use a calculator, or just trust me? Okay, and the answer is definitely not. Definitely not is the right answer. If the teacher did, then all of you were lost, because you need to understand what we're doing today. So let me do the easiest first, and maybe we'll do some others too, because it's that important. It is, I think there should be a whole section on it, because it is like the big application of this stuff. And it's kind of a newer application, so a lot of the books go by old stuff. But I'm not old school. I'm here to help you out. What's going to happen to you when you get into your engineering classes, or when you get into your, kind of chemistry, physics classes that are advanced to upper division. And I want to make sure you're ready for it. So let me give you, it's a basic example. And the only reason why I did basic is that there's no reason to, crunch out a lot of numbers. That's not what I'm trying to show you. I'm trying to show you how to do the math. With the numbers, then you use a computer. And the question is, find the equation of the least squares regression line for the data 3, 2, 5, 1, 4, 3. Okay, so the first thing is, do these points all lie in the same line? Do these 3 points lie in a line?
Yeah, isn't it like m equals 1?
Okay, we could try it. Okay, if m equals 1, then if I
negative.
If I add 1 to 4, I'm supposed to add 1 to 3 and get, no, that didn't work. Do you see?
Wait, no, actually, never mind. I think I read it wrong.
They don't. And you could look at, say you look at the first one, the third, okay, that one has slope 1. Whereas the first and the second one, that has slope negative 1/2. Okay, different slopes. And that's the definition of lying in the same line. It means no matter which 2 points you pick, you get the same slope. All right, but then the next question, and this is the big question for regression analysis, is of all lines, y equals mx. I'm going to write a plus bx. Okay, there's a reason I'm writing a plus bx instead of mx plus b. And we really won't understand that for about 3 weeks. But for now, just trust me, it's better to write a plus bx than it is to write mx plus b for regression analysis. Okay, of all lines, y equals a plus bx, which line is the best fit? So the first thing is, what is what's a comma, I think. That still hates me. Okay, so which line is the best fit? What does it mean to be the best fit? And what this means is consider the distance, the vertical distances, and actually write the sum of the vertical distances and the squared vertical distances from the points to the line. We want to minimize this sum. So I want to minimize the sum, because the idea is if these points were exactly on a line, well, then the distance from the point to the line vertically is 0. And then you'd minimize the distance, sum of the distances, because that would be 0. Now you can't do that. So then we're going to be talking about all different lines and seeing which one is kind of the best fit. Any questions on that? So that's what regression analysis does. So now what I need to do is I need to say, well, let's find the sum of the squared vertical distances from the points to the line. Any questions on this idea? Anyone lost? Okay, so I can talk about, I'm going to call it E for error, is going to be the sum of the vertical distances. All right, well, how do you, the square of the vertical distances. So the way you find the distance is you subtract the y coordinates, because vertical is y. Any questions on what I'm talking about? Again, this is very important. So vertical distances are y's. So the y coordinate of the first guy is a 2 minus, and the y coordinate on the line, if x is 3, is a plus 3b. And then we're supposed to square that because we want the square of the distance. Actually, yeah, square. Any questions on that? Is that how you get the r squared value? Exactly. Exactly. That's how you get the r. That's kind of the idea of the r squared value. Okay. R squared is a little more complicated than what I'm saying, but that's how you start getting the r squared value. That's the idea. Any questions on that? Okay. Yeah, this is all the stuff that you learned, but you were told, oh, the math is too hard for you, so you can't do it. And that sounds right for those who are in stats? It's what I teach. When I teach my stats class, I say, just trust me. Okay. And if you haven't had stats, you don't have to take stats, but you definitely want to learn this kind of stuff. R squared is important. Okay. And then what I do is I do exactly the same thing for the other points. I'm going to copy and paste and change the numbers. So now we're going to have, instead of a 2, we're going to have a 1, and then we're going to have a plus 5b squared. Yeah, it shows up in chemistry. I told you this is This is the most important application in all of everything, not just science, actually. Social science also comes up a lot. But, you know, all those sociologists, they have no idea what the calculus is. They have no chance. But you guys can. That's the difference. Okay. Yeah, definitely shows up in chemistry in a big way. It shows up in every field. Except maybe, I don't know, history. But shows up in everything they call science. That includes, say, social science. Okay, so now we're going to have a y is 4. And we're going to have x. Sorry, y was 3, not 4, 3. And then x was 4. Okay, and that is the sum of the squared vertical error, just vertical errors. Okay. By the way, why do you think why do you think you use the sum of the squared errors instead of the sum of the errors? Any thoughts? Yeah, you're gonna have negative numbers when you do that. And if you just do errors, then you're gonna have absolute values. And what's the problem with absolute values? Because if you just want errors, then this can be absolute values. You want to have negative numbers, you take an absolute value. And what's the problem with absolute values? They can be broad. I don't know what broad is. But there's a big issue. Think about this class. No, absolute values are very specific. Absolute value of negative 20 is 20, period. There's a big problem with absolute values. Who knows it? Think about this class, this year, this academic year. 40 off in the middle, no. Okay, maybe I'll tell you. Absolute value function is not differentiable. Can't do calculus. Can't take a derivative of the absolute value. And that raises all kinds of horrible problems. So the mathematicians said, all right, we're going to use squared errors. And squared errors, then you have no problem with derivatives. Okay, so that's the real reason, is that you could do absolute values, but it is evil when it comes to calculus. Okay, now what do we want to do to get the best fitting line now that we got our error with general A's and B's? So what do we do? Any thoughts? If we want the best fitting line, not just any line, simplify, you could, but simplify is not what I have in mind. Think about the whole point of this class. Plug, not quite. Starts with a G. Yeah, take the gradient. We want to find out the minimum error. Want to minimize that error. Minimizing, let me highlight that word. Minimizing means we need to find the value of A and B such that you end up with a minimum error. And the way you find the minimum is you take the gradient and you set it equal to 0, and that gives you the critical values. Okay, so that's how you get the error. That's how you get the minimal error, is you take the gradient and use the first and second derivative test, basically. So now I can do that. And I can go grad E equals, I know you're used to X and Y, but I want to give you, what's standard in statistics, which are A and B. So A and B are the variables, not constants. And that's something to remember. You're so used to probably that the slope and y-intercept are constants, not in this case. In this case, they're the variables, because that's what we have to decide on. And they could be anything, and we're going to pick the A and B that minimize it. So the grad E is equal to, well, we need to take the partial derivative with respect to A first. And that is going to be, by the chain rule, 2 times A plus 3B. It's 1 times A plus 3B. And then the next one. Oh, no, sorry about that. It is 2 minus. So it's 2 times parentheses 2 minus A plus 3B. I decided to not simplify it. It's kind of good to look at it as it is now. So I'm using the derivative of the square function is 2 times. So it's 2 times that, and the derivative of this is a negative because we have the minus A. And then we're going to have, again, we have a minus 2 times, same thing, 1 plus A plus 5B. And then we're going to have a minus 2 times, and then we're going to have the 3 minus A plus 4B. Any questions on this example so far? Okay, then what do we do? Here's the end. I just found the derivative with respect to A.
Find it respect to B.
Yep, find it with respect to B. And it'll be very similar. In fact, it's worth copying and pasting, if it lets me. And erasing what I can. So with respect to B, the only difference with respect to B is you're going to be multiplying by this 3 and by the 5 and by the 4, because it's all part of the chain rule. Whoops. Let's go times 3, then times 5, and then times 4. Okay. And then what do I do? Yeah, we set that equal to 0, 0. Okay. And I don't think I'm going to waste your time. I mean, if you want, I could, but I can multiply all this out. I can set them both equal to 0. I'm going to get 2 equations to unknown, and I can solve it. Any questions on this idea? Okay, and when I solve it, I'll get my A and B, and that's the A and the B for the least squares regression line. And it's messy. Okay, if you have 100 points, you would never do it this way. How would you do it?
Take a limit.
No? Yeah, I like that one. Use a computer. Yeah, you would never do it by hand or by typing. You just get them, put them in a spreadsheet and use a computer, but it's important to know what the computer's doing. And what the computer's doing is it is finding the minimal sum of squares of differences for that A plus BX. Okay, and this is a least squares regression line. I'm not going to do the whole thing, but we can do the same idea. What if instead we said, you know, this probably isn't linear. Okay, this might be exponential. Does that make sense? Any questions on that idea? And we could say, what is the least squares exponential fit? Where when I say by exponential, I mean y equals, and I'll just use a and b again, a e to the bx. Isn't that kind of a standard exponential equation? Any questions on that idea? And then I do the same idea. Except now, instead of 2 minus a plus 3b squared, I'm going to do 2 minus ae to the b times x. And x was 3. So a 3x, 3b squared. And then I could do the same thing for the others. And the next one will be e to the 5b. And then the third one will be ae to the 4b. And guess what I would do next? Any thoughts? So what I do next if I wanted the least squares exponential? Yeah, I take the gradient. I set the gradient equal to 0. I'd solve. And I get my a and b. And that would be the least squares exponential fit. So basically, once you have this idea, you can do whatever fit you want. Okay. And in the real world, what do you think the hard part is? There's two hard parts, actually, in the real world. Any thoughts? Yeah, one is deciding what kind of fit you want. Do you think this is exponential growth? Do you think it's linear growth? Maybe it's parabolic growth. Maybe it's some kind of sinusoidal kind of thing with a sine and cosine. Basically, this works with any kind of curve you want, but you have to decide what curve is the right curve to use. That is beyond this class, way beyond this class. That's probably graduate level, but pretty cool stuff. And you make big money if you really know how to do it. All AI works this way. Okay, just about all AI works this way, is it decides on the best fit. Okay, and has to come up with it. And then the other big piece that's even harder that you probably wouldn't think about is how much data do you want? I have 3 points here. Well, should you take 1,000 points? You take 100 points. How about 1,000,000 points? And one of the weirdest things is that you think that million would be better than 1,000. Doesn't that sound right? Do you want a, better model of the world? The more data, the better. What do you think? Okay, it turns out that's not true. It's not true that the more data, the better. And again, way, way too hard to explain. Okay. So, and it's not just because it's, a lot of work to do a lot of data. Actually, having too much data causes problems. And again, that's beyond this class, but it is math, and I figured I should mention it since it's the next, I don't know about the next step, but it's one of the next steps in using this stuff. Any questions on this? My guess is that those of you who had stats, are you convinced that your teacher did the right thing not to show you how least squares regression works? Okay, because you are calculus students. Imagine the non-calculus students in that stats class. Forget it. Okay, so that's the old trust us. Yeah, you would have gotten scared. Imagine the people that were not the STEM majors. Yeah, it would have been worse than scared. They would have ran out of the class. Or maybe hit Win or me, whoever the teacher was. Okay, so anyway, that's least squares regression analysis. And to me, it's really important, so I wanted to show it to you. Okay, and it's what we're doing. It's the first and second derivative test. Second derivative test turns out you don't need to do because you always get a minimum. So that's the good news. And that's proofs. So I'm going to move to Lagrange multipliers. Again, we don't have that much to do in this particular section. And that's why I was able to do that one big piece from the last section. The last section had a whole lot, and this doesn't have much. Okay. So as you might guess, who do you think was the person that came up with Lagrange multipliers? Lagrange, yeah. Lagrange. Okay, that's, I think, French. That's why the pronunciation is really hard. Lagrange, I guess, might be the better way to pronounce it. Okay, and here's the idea, is that often you have a function that you want to find the extrema, find the max, find the min, but it's subject to constraints. Okay, so here's a big theorem. And that is, let f of xy and g of xy be nice differentiable functions. Okay, remember, I will never give you a not nice differential function in this class. So if you want to deal with not nice ones, you need to take upper division math classes. So for us, all functions are nice. Sound good? So I don't want to kill y'all. So let's suppose that f and g are nice differential functions, such that f of xy restricted to the curve g of xy equals 0 has a local extrema at the point AB. So that means that AB might be a maximum or AB might be a minimum. Okay, a local max or a local min. That's all that means. Then there exists a number. Who knows how to say this number? This letter?
Lambda.
Lambda. Do you know why we use the letter lambda?
Because there aren't enough letters in the regular alphabet.
No, that's not the reason.
Because you don't want to use L.
Yeah, so we'd like to use L because it's the first letter of Lagrange. L is a terrible letter to use. Why is L such a bad letter to use?
Many things representing it.
At least the way I draw it, because it looks like a 1. Yeah, especially lowercase l looks like a 1. So no one uses L. You'll like never see L used as a variable, or almost never. So we use lambda. Lambda's a good old Greek letter. Okay, and it's called the Lagrange multiplier, such that grad f evaluated at AB is equal to lambda times grad g evaluated at AB. So again, I want you to look at this because this is like the whole point of the whole section. I could prove it. It would probably take about 20 minutes to prove one, and I think you get nothing out of the proof. So if you really want to see the proof, what can you do?
Email you or come to your office hours.
Yeah, probably not. Even better, because I'll just tell you.
Just use the internet and Google it.
Yeah, Google it, or just look at the book. The book's got it in there. But I think the proof is not going to be helpful for you guys. You're not going to learn much from it. So I'm not going to prove it. But do you trust me or trust Lagrange?
Yes, I trust you that it'll take 20 minutes and not have anything I could use today.
Yeah, but do you trust me that this is true? That's all I want.
Yes.
That's what I want. Yeah. You could become a math major like me. I had to prove this at one point. Okay. And this is Lagrange multipliers. It looks kind of messy, but it turns out it's actually most of the time the better way of finding max and min than the other way. The other way is if you have g of x, y equals 0, you can solve for y in terms of x. You can plug that y in to f, and then you can find the critical points. The solving for y in terms of x is often miserable. Whereas this grad FAB equals lambda grad G of AB is usually not too bad. So typically, I'd say 90% of the time that you can use Lagrange multipliers, you want to use Lagrange multipliers. Okay, and the other 10%, then you just do the substitution thing. Any questions on this big theorem before I jump into an example? Okay, one more question for you. Of all fields, which field do you think uses this the most? Yeah, business. Okay, this is the thing in business. In fact, a lot of people say the reason business majors often have to take calculus is Lagrange multipliers, and that's it. That's the whole point. It's just a big rush to get to Lagrange multipliers so that they can do what they need to do in business. Because in business, you often have constraints. Okay, you want to maximize. What do you usually want to maximize, by the way, in business?
Profit,
Profit. But what are your constraints?
cost.
Yeah, cost is sometimes a constraint. Okay, so that's one of them. Labor is often a constraint. Sometimes it's materials that you can only get enough of something. Okay, so there are many, many kinds of constraints that happen in business that make it so that you need to use Lagrange multipliers. But you always want to maximize profit. That's just a business thing. Okay, that's number one in business, right? So just like, sometimes revenue is more important to maximize when you're a new company. But either way, there's always going to be constraints. So Lagrange multipliers are kind of the thing in business. Do you think constraints happen in chemistry? Do you think this happens?
Yes.
Yeah, where might it happen in chemistry?
You might not have enough of a limiting
I like
reagent.
energy, conservation of energy. You heard of that before? Chemistry, physics, which are the same thing. I don't know if you realize that. You may feel like they're different, but they're really the same. So you've heard of the law of conservation of energy? So if you have the law of conservation of energy, then that's a constraint, is that energy needs to be a constant, and subtract the constant, you get equals 0, and then Lagrange multipliers are the way you maximize stuff, okay, or minimize things. Okay, so that's definitely one of the biggies in chemistry / physics. Okay, is that you have that law of conservation of energy, which means that energy is a constant, and that's an equal a number. Okay, any questions on that? Okay, so this does come up in a lot of fields, by the way. So let's go and do an example. So the question is, find the extrema of f of xy equals x squared minus y squared, subject to the constraint y minus x squared equals 0. And we're going to use Lagrange multipliers. You could do this without, actually. This one's not a hard one without. But what do we do? What we've been doing for the last week. What do we need to find?
Second derivative.
Yeah, but I'm looking for a 4-letter word. Yeah, gradient, grad. Okay, gradient is the longer way of saying gradient. We find the gradient. So what we do is we say grad f, let me just write it. Grad f is equal to lambda grad g. So I'm just writing it down without thinking, because I know that's always true when we have a constraint equation and when we want to find the extrema. And then I find grad f. What's grad f? This isn't supposed to be hard. 2x comma negative 2y. Any questions on that? And that is equal to lambda times grad g. What's grad g? Negative 2y, comma. Wait. Grad g is okay. What's the derivative? Yeah, it's negative 2x comma 1. Any questions on that? Okay, so that gives us how many equations, how many unknowns? Okay. Yeah, it gives you 3 equations, 3 unknowns. It may look like 2 equations because you look at this line and you see 2 equations, but there's another equation. What's the other equation? What's the other equation besides what's right here?
The constraint.
Yeah, the constraint. Y minus x squared equals 0. So don't forget the constraint. It's kind of maybe the number one mistake on Lagrange multipliers is to forget the constraint equation. So I'm going to write the 3 equations. And we have 2x is equal to negative lambda 2x, negative 2 lambda x. And then we also have negative 2y is equal to lambda. And we also have that y minus x squared equals 0. Anybody lost? Anyone lost on this? Okay, which is the easiest of these? First, second, or third? The first? I think the first is the hardest, actually. I guess first isn't too bad if you want. I'll use the first just for fun because it's not so bad because you can look at the first and what does the first tell you? I'll use the first since that was the first person. Huh?
It's a line.
Not quite. It tells us 2 things. Okay. One is lambda equals negative 1. Whoops. There it is. But that's not it. What else could happen? I could say lambda's 10 and I'll still get a solution. You want to see it? How about x equals 0? If x is 0, lambda is 10. Do you all agree it works? So be very careful about dividing by a variable. When you do that, you also have to do an or the variable is not 0, or the variable is 0, sorry. Any questions on that so far? Did I lose anyone? Okay, it's algebra. It's real messy algebra. Okay, so we have two cases, right? We have the lambda equals -1 case. We have the x equals 0 case. Let's do the lambda equals -1. If lambda is -1, then what is y? Yeah, y is 1/2. So let me go comma 1/2. Now, if y is 1/2, what is x? Look at the third equation. So if y is 1/2, what's x from the third equation? Yeah, square root. So it's going to be square root of 1/2. Add x squared to both sides, take a square root, and you get root 1/2, or 1/√2 is probably a nicer way of saying it. Is that the only possibility for x? If lambda is 1, so if y is 1/2? Yeah, it could be negative, plus or minus. When you take a square root of both sides, you get the plus or minus. And don't forget the plus or minus. So it could also be negative 1/√2, comma 1/2. Any questions on the lambda equals 1 piece? Okay, then there's the x equals 0 piece. If x equals 0, what do you know about y?
Y is also 0.
Y is 0. So you also have 0, 0. Any questions so far? Because we're not done yet. Okay, these are the possible extrema. How do you decide what the max is and what's the minimum? Do we use the second derivative test?
Yeah.
One more guess. No, we don't need to. These are all the possible max and mins, right? So how do you find what the max is? And the min? No, you just plug them in. Plug them into F. And let's look at it. That's why I copied and paste. That way I could write F. So F of 1/√2 comma 1/2 is, well, we get 1/2, right? 1/√2 squared is 1/2 minus 1/4. 1/2 minus 1/4 is 1/4. I could do the same thing with the negative 1/√2 comma 1/2. I get exactly the same thing. Squares kill negatives. I'll write F. And I could do the same thing with 0. And F of 0, 0 is? That should be really easy.
0.
Yeah, 0. So what's the max and what's the min?
1 over root 2, 1/2 is the max as well as negative.
Okay, so the max itself is just 1/4.
Oh, okay. And then
If I
min is
asked you
0.
where is the max, that would be 1 over root 2 comma half. If I ask you what is the max, that's 1/4. It's English. So that's the max. The min is?
0.
Min is 0. Any questions at all on using Lagrange multipliers to come up with this?
All right, since we're within a constraint, these are considered global then, right?
Yeah.
Okay.
Yeah. So these are global. If you want to write global, you can. But usually when you're doing a constraint, you don't need to, because when you're within a constraint, it's period. It's global. You know,
Well, that's kind of,
if you have the word constraint, then that's got to be global.
okay. Well, that's kind of what I was talking about earlier. I feel like just the question kind of tells you whether or not we're talking about the relative or global, but yeah.
Now, the thing is, if you're in a constraint, then it's global. If you're
Right.
not within a constraint, it could be either. Then it depends what you want. Does that make sense?
Yeah, yeah, I absolutely understand. I think it's
Yeah.
just splitting hairs.
Yeah, it might be splitting hairs, but I'm just telling you how people use things. And that's how people use it. Any questions on this example? Okay, let me give you a note. And the first is Lagrange multipliers works for functions of more than 2 variables. So note Lagrange multipliers say grad of f equals lambda grad of g. So if we had 3 variables, you wouldn't have a comma b, you'd have a comma b comma c. That's the only difference. Does that make sense on works the same? And you wouldn't have f of xy, you'd have f of xyz. Any questions on that? So everything's exactly the same, but you throw in a comma z or a comma c, depending on what you're looking at, and it still works. Do you think 3 variables is harder than 2 variables? What do you think? It's much, much harder, okay? And it's not harder because of calculus. Algebra. 2 equations, 2 unknowns is so much easier than 3 equations, 3 unknowns. Does that make sense? And 3 equations, 3 unknowns is a whole lot easier than 4 equations, 4 unknowns. It just gets harder and harder and harder as you go. So I want to give you that big warning that this stuff gets brutal algebra-wise. So the examples, of course, are set up to be nice. In the real world, you got to use fancy stuff with the computer. But let's do a not fancy example. And that is find the distance from the origin to the surface, x, y, z equals 8. Any questions on the question? Okay, so if we have a point, x, y, z, then how do we find that distance? I can call the distance f, just so we don't get confused with d's. F of the point x comma y comma z. How do you find the distance from the point to the origin? So if you're given a point, yeah, square root of x squared plus y squared plus z squared. But let me tell you something. If we want to find, so finding that distance means what's the minimal distance? So if we want to find the minimal distance from the point to the from a point to the origin, then we could look at the minimal square distance and it'll be the same minimum. Do y'all agree? Distances are always positive. Squaring isn't going to change which one's the minimum. Any questions on that? And the reason why I want to square it is so I can get rid of that square root. So f of xyz is going to be x squared plus y squared plus z squared. Where today have we seen something very similar to this? Well, we just learned, not what we first learned, regression analysis. Regression analysis is the minimum square distance. Does that make sense? So this is just another way of saying regression analysis without like saying the word regression analysis, but it's really the same thing. Okay, so we have f of x, y, z equals x squared plus y squared plus z squared, but we're on the surface x, y, z equals 8. So guess what we need to do? Think French. Yeah, we use Lagrange multipliers. We take the gradient of f. That's going to be 2x. Hopefully it's easy for you too. 2y, and the gradient should be easy for f of x, and 2z. We set that equal to lambda. And we take the gradient of x, y, z equals minus 8 equals 0. Okay, because subtract the 8 to make it equal 0, but the 8 doesn't matter. So lambda times, we have yz, comma, we have xz, comma, and then we have xy. Any questions on that? Okay, so now we're going to have a bunch of equations. We get 2x equals lambda yz. We get 2y equals lambda xz. We get 2z equals lambda xy. And we still have xy equals 8. Are you convinced that Lagrange multipliers can get really rough? Algebra-wise? Okay, and hopefully you're convinced that the algebra is the harder part, not the calculus. The calculus was pretty easy. Taking the derivative, at least for me, that was like nothing. But the algebra you got to think about. Nothing looks so great. So what I'm going to do actually is I'm going to solve for lambda in the first 3 equations. Turns out to be probably the easiest way of doing this. So I'm going to say lambda equals, and we get 2x over yz. And lambda is also equal to, we get 2y over xz. And lambda is also equal to 2z over xy. Any questions on that? All right, so now the trick, and that's kind of what this is. It's all about algebra tricks. Is when you have fractions. Fractions are what make this hard. Do you agree? How do you get rid of fractions when you have equalities?
Cross multiply.
You can. That's not the easiest way in this case. Yeah, multiplied by the LCD. So multiply by XYZ. So I'm going to multiply all of these by x, y, z, and I get 2x squared equals 2y squared equals 2z squared. Any questions on doing the algebra? There it is. Okay, now that I have 2x squared equals 2y squared equals 2z squared, the twos don't matter. You can divide all of it by 2. You get x squared, y squared, and z squared are all the same. So that means x and y and z are all the same except possibly plus or minus. So if x, y, and z are all the same except possibly plus or minus, I could put that into the x, y, z equals 8. And now I can say plus or minus x cubed equals 8. So what do I know about x? X equals 2 or -2. So in particular, x, y, and z are all the same except plus or minus. So I get -2, comma, -2, comma, -2, comma, and I'm just going to go dot. I'll do one more and then dot, dot, dot. We have a -2, comma, -2, comma, 2. Now I'll use dot, 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 and then 2, 2, 2. In other words, they're all 2s with that they might be negative. So there's 8 different ones of these. And I'll write 3 of them. But here's the good news. It doesn't really matter whether they're positive or negative because our f of x, y, z is x squared plus y squared plus z squared. And that means we take 2 squared plus 2 squared plus 2 squared. What do you get? $12. Okay, now that was a square distance. So the minimal distance, or the distance, is the square root of 12. Any questions? Any questions on this example? Okay, let me do the last theorem, and I'll maybe quickly do another example with it. And that is basically if you have a function of 3 variables subject to 2 constraints, g of x, y, z equals 0 and h of x, y, z equals 0, then you get grad f of x, y, z equals a times grad grad g of x, y, z plus b times grad h of x, y, z. Okay, so what it says is that for each constraint, you give it, you multiply by a constant and you add them all up. Okay, so now we could do kind of the same idea. Now we could say, well, what is the minimal distance? Or what is a maximal distance if you're going to intersect x, y, z equals 1 and x squared plus y squared plus 2z squared equals 4? So kind of similar to the last question, but now we have 2 constraints instead of 1. So what we do is the same thing. We take the gradient of f, 2x, comma, 2y, comma, 2z. We set that equal to a times the gradient of g, which is yz, comma, xz, comma, xy, plus b times the gradient of h, which is 2x, comma, 2y, comma, 4z. Okay, just to note, how many equations, how many unknowns do we got? How many equations, how many unknowns? Okay. It's actually much worse than what you're saying, huh? It's 5 equations and 5 unknowns, right? Because the constraint equations are constraint equations. The unknowns are x, y, z, a, b. So 5 equations, 5 unknowns. That doesn't mean it can't be solved, but it means that, you might be crying a bit. So let me just write them down. I don't know if I have time to finish all of it, but we get 2x plus ayz equals ayz plus b 2bx. And then we get 2y equals axz plus 2by. And then we get 2z equals axy plus 4bz. And then we also have xyz equals 1. And we have x squared plus y squared plus 2z squared equals 4. Okay. And I don't think I have enough time to solve these 5 equations and 5 unknowns, but can it be done? Yeah, it can be done, but that doesn't necessarily mean it's easy. Okay, there's a lot of work to do, but in the minute or two, I don't think there's enough time to show you the whole, set of algebra. But it's just algebra, but it's like nightmare algebra. Does that sound right by looking at this? So nightmare algebra is my thing. Okay, and imagine if you had, instead of 3 variables, imagine if you had 6 variables. You just use a computer. You don't think about doing this by hand. Okay, so it does get messy. It gets really messy in terms of the algebra. And hopefully you're convinced by looking at this. But the main thing to note is that whenever you have a function you want to maximize or minimize with constraints, then you take the gradient of the function equals the sum of constants times the gradient of the constraints. Okay, so I did 3 variables, 2 constraints, but you could do 100 variables, 20 constraints if you really felt like it. Okay, and again, you would never do that by hand, use a computer, but the point is to understand it can be done. Because in the real world, what you do is you have something really hard. You don't have to actually do all the algebra. But if you don't know what to do, then you can't tell the computer what to do, and then you can't do it. Does that make sense? That's real world math versus, this math, where we keep everything simple, but in the real world, it's not simple, but you let the computer do the really messy work and you do the thinking work. So that's kind of how life works. So I'm going to stop my share and stop the recording.